Linear independence, blah, blah, blah. Okay, here we go. So here now we have three vectors, three-dimensional vectors. We want to know if it's linearly independent. And there's a statement over here, columns of matrix A linearly independent if and only if the equation AX equals 0 has only the trivial solution. So that has a lot of follow-up too that we can match up. But what did I mean by that? I mean that statement has a lot of implications to other things like pivot columns and solutions and stuff. So let's take a look at this. And what we'll do here is we'll make a matrix out of these as if they were column vectors. So let's let A equal to the matrix 0, 0, 2, 0, 5, negative 8, minus 3, 4, 1. And well, this looks like if I just switch the first and third rows, right, I can have it in row echelon form already. Not necessarily reduced row echelon form, but at least row echelon form, just so we can get an idea of the pivot column. So if we switch that, we're going to get 2 minus 8, 1, 0, 5, 4, and 0, 0, minus 3. And so here, if we have pivot columns, pivot in all columns. So if we were to row reduce this, we're going to get ones in the diagonal and zeros everywhere else. So I won't do it. I'll just say dot, 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 RREF. Which is to say that this only has a trivial solution. Because remember, if we do this, we pretend that there's zeros in the augmented column, which we didn't write. But if we pretended that there's zeros in the augmented column, we would have x3 is equal to 0, x2 is equal to 0, and x1 is equal to 0. And so that's the only solution we can get out of this. So if we have a pivot in all the columns, then we can conclude that it's only the trivial solution. And according to this, if and only if statement, because we have only the trivial solution, we can conclude that these vectors are linearly independent. Therefore, vectors are linearly independent. All three of them are linearly independent from each other, yes. And the whole thing would fall apart, yeah. Yes. So the definition of linearly independent is this, to say that the only way that if you write them as a linear combination of each other, then the only way you can get 0 is that if they're all equal to 0. So let me write that out real quick, and I'll get your question. So 0, 0, 2 plus blank times 0, 5, negative 8 plus blank times minus 3, 4, 1 equals the 0 vector. The only way this would work is that if we put zeros in the blank. So only solution. Now, if they were linearly dependent, then we can get 2 or maybe all 3 of them to equal to a number that's not all equal to 0. And then in that case, then it would be dependent. Geometrically, we'll take a look at it, yeah. Yeah, this is, when they say 0 vector, that's, That's the zero vector, yeah. We would have a free variable when we get to this point here. That could be anything. And we could take a look at an example of that. And, oh, Matt first, and then. Okay, so geometrically speaking, I mean, we can, I think we can draw these vectors on graphing paper, on my graphing program. Yeah, so because it's 3 dimensions, we can still view it, so there's geometric significance for this. Actually, there's geometric significance for everything, but um, the next one is 0, 5, negative 8. 8. And then minus 3, 4, 1. So the significance between these 3 vectors being linearly independent means that they're not collinear. If all 3 of them were collinear, then they would all lie on the same line, and they would definitely not be linearly independent. But now if you have 3 of them, you can have 2 of them to be linearly independent, but the third one might depend on the other 2. And in that case, then the 3 of those vectors could possibly lie on the same plane. Okay? And if there's 3 vectors lying on the same plane, then it is dependent. Does that make sense? So what I could do is I can make a plane out of these 2 vectors at a time and see that they're not all going to be on the same plane. All right? It's a lot of work. But that's the idea. Does that answer your question? So, more or less, yeah, right?
All the numbers have, it has to have like all pivots in each column.
Yes.
Okay, and then you know how you had the reduced row echelon form when you wrote like the dot dot dot
Yeah.
the zero. Do you know like is that actually the answer, or you just like
Yes.
that's for the sake of?
Yeah. So
like eventually it'll work out to that.
if you reduce everything, it'll eventually work out to this. Correct. I mean, if this thing doesn't have any pivot columns, then this is what's going to happen. Or if this thing did not have any free variables. It has pivot columns in all the columns. It'll end up like this. Um, so let me see if I can just take a quick picture of this. There it goes. So we can make a note to say that geometrically the 3 vectors, and just so we're clear, these are 3 vectors in 3D, are not collinear, not coplanar. You know what I mean by coplanar, right? They don't lie on the same plane. Um, I guess period. I don't know what else to say. So they're not collinear, not coplanar, and then they would be linearly independent from each other. Now let's see if we can come up with an example where they're linearly dependent. I don't know if this first one This first one? I don't know. Let's let me check. Oh, do you guys have your MATLAB assignment done? And did you guys check how many? Three or yeah? So I didn't give a due date for that. For some reason I couldn't. So let's make it due by tomorrow. I mean, most of you are done with it, but if we make it due tomorrow, then that would be good. Was the worksheet due today? It was due on Monday, yeah. So it'd be like um, a couple of days after. I don't know. Yeah. 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 Wow. All right, so this doesn't work out. I mean, it is linearly independent, and so let's just make up another set of problems that are linearly, or a set of vectors that are linearly dependent. And for this, I'm going to ask for a couple of vectors, and then we'll make up a third one. So vector, 2, 3, 1, and then another vector. Yeah, no. And so what I'm going to do is I'm going to, find the linear combination so that they would work out. So I'll say 9. What am I doing? Is it 24? No, 2 times 3 is 6. So it's 12. 2 times. I don't know. Let me check. Okay. So this looks like it made the whole bottom row disappear. So that means I'll have a free variable here. Okay. So let's pretend that we didn't know that, and this is our example, and let's see. Well, that's how I write exams. Try things out, and then I'll just go back and do it. You should try to figure out how your professor thinks so that you can anticipate their exams. That's what you should do. Yeah, and it'll work. All right, so to check if this is actually uh, linearly independent, what we would do is we would go ahead and do our matrix. We'll let A equal to 2, 5, 9, 3, 6, 12, 1, -7, -5. And then we'll do some row reducing to see what we can work out. I might want to, I don't know if it matters, but I want to put that 1 up on top. And so let's do a quick switch, R1 and R3. I mean, you could do this any way you want. But I'll, I'll give you a quiz on Monday about row reducing. So just, and no calculators or anything like that, just doing everything by hand. Yeah. No, no, no. I mean, you should have that with you all the time, anyways, in case. Oops. Or like Alan said, you take a picture of it, then you have it on your phone. I don't know. It should, yeah. Yeah, so I might need to get a little closer to you to scan, but then you would have it. What? Tried? I don't suggest that. So let's go ahead and get our first column figured out, and it looks like if I just multiply the first row by by -3, and then add it to the second row, and then I'll replace my second row. And I want to do 2 steps in this step because there's room for it. So this is going to be -3 plus 3 is 0. -3 times -7 is +21. 21 plus 26 is 27. -3 times -5 is +15. 15 plus 12 is almost 30. 27 also. And then here's where I get to do the other step because I'm not touching the bottom yet, so I'll mess with it now. -2 times R1 added to R3. I'll get rid of that 2 over here. So that's -2 times -7 is 14. 14 plus 5 is 19. -2 times -5 is +9. No, +10. +10 plus 9 is 19. So I got 19, 19 in the bottom row, 27, 27 in the second row. So if I just do whatever is appropriate there, it'll knock out the whole bottom. Right? Multiply the second row by 19, -19 over 27 or something. So I'll say that. -19 over 27, multiply that with the second row, add it to the third row. 1, -7 minus 5, 0, 27, 27, 0, 0, 1, or 0, 0, 0. So here I have a pivot column on the first and second one, and then I have a free variable on the last column. So then that tells me that I don't have a set of linearly independent vectors. So these vectors are dependent. I don't know which one's dependent on which one, but all I know is that if I were to write these vectors out as a linear combination, 2, 3, 1, 5, 6, -7, and 9, 12, -5. That I can actually find non-zero numbers to put in these blank spaces to make it work. And it doesn't matter what they are. I can have an infinite number of solutions for this. I have a free variable, so I know that I'm consistent, and I know that I can find an infinite number of variables here. And I think the way I made this work is that I multiply this by 2, I multiply this by 1, and then subtract it. I think that would work. But again, if I multiply this by 4, 4 or 2, -2, then that should also work. So I have like an infinite number of combinations that I can put. In any case, vectors are linearly dependent. So now that I know that they're dependent, I can look at them and say, oh, they don't all fall on the same line, but somehow these vectors will all be on the same plane. So let's take a look at that and see how that would look like graphically, because we have the power to graph stuff. So I'm just going to use the same template over here and graph. And our last one is so it's hard to see, but I mean, if you look at it at the right angle, you can see that they're in the same plane. But let's actually find the equation of that plane. And the way I'm going to do this plane is I'm going to write a linear combination, or not a linear combination, but a parameterization of these vectors. By that, I'm going to write this. I'm going to write two of them. I'm going to write two of them as a linear combination of each other, or yeah, linear combination. And I'm going to use a parameter t and s. I think I need to use u and v though. So if I do that, I'm going to get a plane. In this case, it's just a piece of a plane because I'm only letting my u and my v equal to go from 0 to 1. But you can see that that third vector is in between those other two vectors, right? If I actually want to capture that, what are the coefficients again? I need to multiply this 2, 3, 1, 2, and then 5, 6, -7 by 1. So if I let my coefficient of 2, 3, 1 go from 0 to 2 instead of 0 to 1, then I can see that vector actually get covered, and they're all in the same plane. Technically, the plane goes on forever, but if we just chop it off there, we can kind of get a clearer picture, clearer result. Any questions? Yeah. Because they're linearly dependent, yes. Well, if all three of them are linearly dependent, then the three of them will be coplanar. This is in 3 dimensions. If we go higher dimensions, then the words and phrases that we're using would be a little bit different. But yeah, if two of them, I mean, if all three vectors are supposed to be linearly dependent in R3, then they all would be sitting in the same plane. Okay. I don't know if this is a good picture to get, but we'll put it in our notes. Unless you can draw it. Can you draw these pictures? I like to draw pictures. Can't wait to get to Calc 3 again. Well, if you draw enough of them. Yeah, those are cool. They're like the conic sections, except 3D. All right, let's take a look at some other questions they might have for our linearly dependent stuff. Oh, true, false. These might be good quiz questions. Let's do let's do one of these guys. H, where they throw in an H. It says find the values of H for which the vectors are linearly dependent. Let's just do number 11. So for which values of H are they going to be linearly dependent? Hmm. You want to have a we want to have a free variable. So we want to have pivot columns in 2 out of 3, or maybe we generally we want to have a free variable if we want this to be dependent. All right, so let's get it set up. So let's let A equal to 1 minus 1, 4, 3 minus 5, 7, minus 1, 5. And this is the H that we're looking for. And we're going to force this H to be something so that it's going to be a free variable, which means we're going to probably want a whole row of zeros in the bottom. All right, let's go on and do some row reducing. I think if I just add row 1 and row 2 and replace row 2, that would make this go to 0. So we add, I'm going to get -2. We add, I'm going to get +4. And then for the bottom one, I'm going to multiply the first row by -4 and add it to the third row. That would make that 0. So that's -12 plus 7 is 5. +4 plus H. And then let me take an extra step because we can just multiply the second row by a half, -1/2. 1, 3, minus 1, 0, 1, -2, 0, 5, H. Or that might just make things a little bit easier for us when we get rid of that last one. So we're going to multiply the second row by -5 and add it to the third row. -5. Okay, so then this is +5. All right. So we have 1, 3, -1, 0, 1, -2, and then here's where we get 0, 0. And then +5 times -2 is -10. And so -10, we add that to 4, -6, right? Okay. So we basically want a whole row of zeros, which means H minus 6 has to be equal to 0. So H minus 6 equals 0 will make the vectors dependent. If H does not equal to 6, then the set of vectors will be independent. Okay. Any questions? Yes. If h is equal to 6, then it's dependent, correct? So you can imagine the two vectors, the first two vectors is a couple of vectors in space. And then the third vector, when h is equal to 6, it's going to be on the same plane as those other two. And when h is not equal to 6, there's an infinite number of possibilities for it to be linearly independent. Okay? All right. Let's check out these true-false questions. I don't know if I want to do them. By carefully reading the text. Does anybody carefully read the text? Somebody would. Thanks, Al. All right, let's see if we can make sense out of these statements. Um, oh, I thought there was only one of them. And there's 8 of them. Apparently not. I just want to do number 21 then. Um, all right, exercise. Mark each statement as true or false. Justify. Let's look at 21A. The columns of matrix A are linearly independent if the equation has the trivial solution. Is this true or false? False? I think it's true, but why? What? Ah, so if you want to get really picky about it. Yes, yes. Calm down. You're right, Nate. All right. Uh, so this ax equals to 0 always has a trivial solution, but it could also have other solutions. And so what Nate was saying, if the word only was here, has only, then it would be true. But otherwise, the statement is false. False. Ax equals b or ax equals 0 always has trivial solution. I don't know what's happening. I did. I don't know. I just, it's the way I'm writing. Okay, okay, all right, all right, all right. False. Ax equals 0 always has the trivial solution. All right. Okay, second one. If S is a linearly dependent set, then each vector is a linear combination of the other vectors in S. And each vector is a linear combination of the other vector in S. So that means if I take this vector, if they're linearly dependent, then I can take this vector and write it as a linear combination of these two. And I could take this vector and write as a linear combination of the other. So that's true? Yeah, but no. Yeah.
I think that first part about them being in the set would be very important.
The first part that they're in the set is important.
Because also say that the extra vector, the other combination of the other two can be. Since it's within that set, then you might be.
Um, yeah, but if it's equal to 0, then you can solve for, like, move the other vectors around. Yeah. Linearly dependent, right? Yeah. But see, we're stuck in R2 and R3, but if we go to Rn, I'm trying to think of weird things that can happen in Rn. Like the set might have one vector and another set of vectors that are dependent, but those other vectors might not have anything to do with this first vector that's independent from them. Right. Yeah. So that would be an example where it wouldn't work. Right. So I don't know. So at least one. So at least one doesn't mean each vector. So the example that Pedro just gave is that if we had 1, 0, 0 and 2, 0, 0 and 0, 0, 1. So the whole set, if we consider this whole set is linearly dependent, right? But now I'm asking every vector in this set has to be able to be written as a linear combination of the other two. So the question is, can we write 0, 0, 1 as a linear combination of 1, 0, 0 and 2, 0, 0? And the question is, well, can we fill those in with numbers to make them equal? And the answer is no. So when they talk about a linearly dependent set, they're looking at the set as a whole, and then pieces of them might be independent, and then you can have two that might be dependent that might not have anything to do with the third one. So that's why it was false. I think I want to move on now. So you guys can figure out the rest of them. That was too hard. So we're gonna move on, I think. I think we're ready to move on. Linear independence. Oh, there's one more theorem about let's see if we can make sense out of this theorem. Oh, that's what you're just saying. So an index set of two or more vectors is linearly dependent if and only if at least one of the vectors in S is a linear combination of the other. So that's Ali, when Ali said this, there's the word at least here, at least one of the vectors, not necessarily all of them, but you can take one of those vectors and write it as a linear combination of the other two. And they try to say this, I don't know if this is an attempt to make it easier, but this is an attempt to make it mathematically more readable. If S is a linear dependent set and V1 is not equal to 0, then some Vj, where j is bigger than 1, is a linear combination of the first set of vectors. Yeah. Yeah, well, the j is just an arbitrary number accounting to the other points. So you can write your set of vectors that are linearly dependent, and then you can go from one to the next as a linear combination of the previous ones. Yeah, they should be linearly dependent from each other. This is, yeah.
So based off that, like the example we just did,
Uh-huh.
because it was linearly dependent, that means that even though we just proved that like whatever the thing in the question was false, one of the combinations of like two of them still has to be like a combination of the two. If that makes sense.
Yeah.
Okay.
So in this example, if we take a look at this, this is saying if it's linearly dependent, then for if v1 is not equal to 0, then some vj, let's say j is equal to 2, where j is bigger than 1, is a linear combination of the preceding vectors. So v2 is equal to 2 times v1. And so that's what they're saying. And it doesn't say anything about anything further beyond that, because there might be some other vector, like v3 in this case is not a linear combination of the other two, but at least there's one more vector along the line where you can write that vector as a linear combination of the other vectors that you looked at before, but not every single vector after that. Yeah.
So could you say that like v1 is a combination of v2 times 1/2 for weight, and then v3 times 0?
Yeah. 0 times v3. So in fact, in terms of the definition of linear combination, um, you can write not all zeros for these coefficients. You can fill in the blank with some values to make this equal to 0, right? As long as they're not all zeros. So this one will have to be 0, but that's okay because the other two won't be zeros. So if I call this negative 2, I guess, and positive 1, or 1 and negative a half, or whatever other combinations. So here you have not all zeros that make this thing equal to the 0 vector. I guess I should put a vector here. Okay, that's what that theorem says. So our statement here is still false. All right. Any questions? So linear independence, you should really try to internalize this idea. I mean, it's mathematically, I think it's, I don't know. If you can see the graphics in 2 and 3 dimensions, you can kind of see it, but then to try to extend it to higher dimensions, you have to rely on these other. I think so. I think we're going to go, some of our matrices will go into 4 and 5 dimensions. Yeah, our matrices are bigger, that's all. But same process, row echelon, and then you see if there's any free variables, and then get the same results. All right, let's go to the next section, transformation. So linear transformation. Well, before we get into the linear part, let's talk about a transformation first. A transformation is a function, essentially a function. Um, and the function, it takes an input and an output. And the whole idea is that it assigns a unique output. That's what a function was. And so instead of going from a real number to another real number, like x squared going from r to r, here we're allowing ourselves to go from a vector space to another vector space. We have the domain and range, except instead of what we know as range, they call it a codomain. And then on top of that, um, they have, I guess what we call it as range is an image. So there's like four definitions happening here. So let's take a look at back in pre-calculus, our simple example of like x squared or something. Um, this is not what we're going to go into, but if we can relate it to something that we know, then we might be able to get a better handle of this idea of what a transformation is. So this is a function that we all know of. We all know the shape of the function and stuff like that. But we can also take a look at this as our very, very, very simple transformation. And this transformation, to be technical, uh, goes from the set of real numbers and outputs the set of real numbers. But if we look carefully, we're going to see that the output values don't cover all the real numbers, right? We only get the positive, or we also include zero. We only include zero and all the other positive values, and we not include the the, the negative numbers. And so we can, there's some, and the domain is all real numbers. We can put any real number in there. And so we can say that our output actually is 0 to infinity, and we can denote it in several ways. We can say y is bigger than or equal to 0, or we can reuse this set notation with brackets and parentheses. So let's take a look at the details of this and see the relationships between the transformation as we're defining it here. So our domain are the set of inputs that we can put into this function. Our codomain is the set of all possible outcomes and the place where all those possible outcomes live, whatever that means. And our image is all the possible outputs that come out. So you see the difference between the codomain, sometimes called the range. See, it's tricky because sometimes this is called the range. Sometimes the codomain is called the range. And so I think this is why they pulled away from the word range, because the range can be used interchangeably Actually, codomain can be used interchangeably too. But in any case, our image is the exact values that get hit by something in the domain. And everything else that doesn't get hit, including those that do get hit, is going to be our codomain. Okay? You see the difference between codomain and image? Yeah. All right. So because we're talking about transformations now, the transformations will be mappings from not just a real number to a real number, but we're going from a vector space to another vector space. The idea of a codomain just means all the, the set that you're going to get, and the image would be all the possible outputs that you get. So there's a slight difference there that we're going to try to see if we can get straightened out. All right. So that's the general idea of a transformation. Now, a linear transformation is essentially a transformation that follows a handful of rules. Two rules, really. I don't know if this is written in one or... Here. Let's do a linear transformation first, and then we'll talk about some of the examples. So what makes it linear is that it follows two main properties. It's additive in the scalar multiple properties. So the transformation, if we call T our transformation, that's like F back in pre-calculus days. This time, since we're calling it transformation, we'll call it T. So the transformation of a sum is going to be the sum of the transformation of those two vectors. And then the transformation of a scalar multiple will be the scalar multiple of the scalar times the transformation itself. Now, these two properties should look familiar. Do you remember seeing this anywhere in your calculus? What type of transformation, let me change the word from transformation to operation. What type of operation have you seen before that follows these two rules? Not multiplication, derivatives, and there's one more, integrals. Integrals and derivatives follow this. You might as well guess derivatives and integrals, right? But the derivative of a sum is a sum of the derivatives. And if you have a scalar times a function, the derivative of scalar times a function is equal to the function times the derivative of that function, or the scalar times the derivative of the function. So we've seen this in derivatives and integrals. Integral of u plus v is equal to integral of u plus integral of v, and c times u, the integral of that is equal to c times the integral of u. For example, derivatives work the same way, so instead of using this integral symbol, you put the ddx symbol or whatever, then it'll be the same thing, right? And so we've seen this, and it turns out that the derivative and integral are examples of also linear. They're not really transformations, they're operations. I mean, they could be transformations if you look at functions as vectors. Anyways, just think about that. So a linear transformation has these properties, and there are examples of transformations that don't work with these properties. But for those that do, we can actually express the transformation as something. So these are examples of basic linear transformations. Oh, there's more stuff. Let me do that. It follows immediately that. So it follows immediately that the linear transformation of 0 goes to 0. So for this to be a linear transformation, it has to map 0 to 0, 0 vector in the domain into the 0 vector in the range. And these vectors, these 0 vectors, don't have to be the same size, right? If we have a transformation that goes from R2 to R3, then we're talking about the 0 vector in R2 that's 0, 0 versus a 0 vector in R3 that's 0, 0, 0. And also, if you have more than 2 vectors that you're adding and scalar multiplying, what is this called again? It's a linear combination. Oh, right, you guys got that phrase down, right? If it didn't flow right out of your tongue, then keep practicing. If we have a linear combination of more than 2 vectors, then we can apply the rules of scaling out and then adding a linear combination. And remember, the scalars can be negative, so we can just deal with that separately. So, all right. So those are just immediate consequences. And so now let's actually take a look at some examples. And we're kind of giving away a bunch of examples already here. But these are, again, they're just examples. So a matrix multiplication is essentially a linear transformation. So it turns out that if you do have a linear transformation, you can write it as a matrix. And some basic transformations, projection transformation here is an example of projection transformation. Takes a matrix A and then projects it onto something. A shear transformation is a 1K01 vector or matrix. Contraction or dilation takes a K00K and then a rotation transformation. Let's take a look at the first one, the projection transformation, and see why this is called a projection transformation. So let's dig deeper into this and find out its domain range and stuff like that. So as a matrix multiplication, what we're doing is let's let x be the vector x1, x2. Actually, let's use xy. I mean, you can use x1, x2, but if we're going to take a look at this in 2 dimensions, we might as well look at xy. And let's see what happens when we apply a times x. And so when we apply this, we're going to get another vector out of this, right? Do you know how to matrix multiply? Did we talk about that? We talked about applying a vector, right? I think it's something like 1 times x, 0 times y, and then 0 times x plus 0 times y. Anyways, it looks like we end up getting a vector, another 2-dimensional vector. So this would be x and 0. So let's take a look at A. A is a transformation that takes, what's the input? What did we input? A vector in R what? We took a vector in R2, and then we outputted a vector in where? R2 also. I guess it says that because that's R2 to R2. So we can say that the domain and the codomain, that's codomain. There's an I in there somewhere. The domain and codomain are both R2. Now, can you imagine what the image is? The image is a little bit different because not everything in R2 is going to get hit. Matt, what do you think the image is? Positive? I can have a negative x here. That would might give something that's negative. So whatever this thing looks like, it's going to get squashed down into the x-axis. That's why it's called a projection. Because, yeah. Yeah, it's a shadow on the x-axis, so it's going to project it down to the x-axis. 0, 1, 0. Oh, yeah, yeah. Okay. So this is an example of a linear transformation. Now, we didn't actually prove that it's a linear transformation. We know that this is a transformation, and the transformation satisfies, not that it satisfies, but it's a mapping. We've identified the domain, the codomain, and then the range or the image. But now let's actually show that it's a linear transformation. And the way to do that is to show that if we add two vectors, then our resulting would be the transformation of those two vectors. So let's take all these out for now. We'll come back and do more examples of these actual transformations. But to show it's linear, what we need to do is we need to show those two things. We can actually, make it compact and you just show one thing, but let's show the two different things that we need to show. The first one is that if we take two vectors, and for these two vectors, I'm going to have to call them x1, y1 plus x2, y2. So those are my two vectors. And if I were to take those two vectors and apply it to A, then I should get, in the end, A x1, y1 and A x2, y2. So let's see if that happens. So A is 1, 0, 0, 1. And then this is going to be, I'm going to add these two vectors together, x1 plus x2, y1 plus y2. So these are just the scalars, or each of these are just scalars. So let's apply it to the matrix. So wait, sorry, this is 0. All right, let's apply it to the matrix. The first one is going to be 1 times x1 plus x2 plus 0 times y1 plus y2. And then the next one would be 0 times x1 times x plus x2 plus 0 times y1 plus y2. And I'm not going to write all that out because it's just all going to be 0 anyways. And then it all simplifies to just x1 plus x2 and then 0. Now we can kind of take that apart, or we can just meet in the middle over here when we're trying to prove something. I'm going to, I don't know if this is a good thing to do, but I'm going to write it backwards. So this is what I want in the end, right? And so I can write that as just the matrix times each of these vectors. And then I can perform the matrix multiplication for each of these vectors. And then see that this is actually equal to x1 plus x2 and 0. And then those two are the same, so this string of inequalities must have been true. And then we could do the same thing for constant times xy. And so, yeah, you should check for both conditions to show it's linear. So if you do this with a multiplying by a scalar, then we'll see this. This is going to be a true statement which satisfies our, just instead of a t, instead of an a there, you can replace it with a t, and it looks like just this second condition for our criteria for linear transformation. Okay. All right. So next time we're going to show more pictures of how the transformation works in 2 dimensions, and then we'll extend our ideas beyond just R2 to R2. But before we do that, we're going to have a quiz on Monday, right when you get in. So quiz is going to be at the beginning of the class. The quiz will be row echelon, doing a matrix in row echelon form. No multiplication, none of that stuff. So this is a quiz that I should have given you a long time ago, and I forgot. So reducing. No, no, you do it on pencil paper. I want to see the steps and stuff. Oh, so if you didn't give this to me, if you're in the other class and gave it to me in the other class, that's fine. But if you haven't given it to me, this is your 1 extra point on the test. So I'm terrible with